Introductory lecture on machine learning to deep learning. In this lecture, I'll explain what is machine learning and why it is so popular now. I'll also explain what is deep learning and why it is needed to tackle kinds of problems that deal with pictures, text, and speech. Thank you. Machine learning, basically, I'm going to describe in terms of this cartoon. I'm sure that all of you are familiar with Gilbert. He does produce some beautiful cartoons, and many of them are really timely and very topical. But machine learning basically is creating systems without explicitly programming them to make decisions. And generally, in order to create those systems, you need a large number of examples. And using those examples, system kind of learns on its own and tries to perform an optimization so that whatever decision making you need to do, that decision making is optimized. If you look into the literature, whether technical or commercial or business literature, or even social literature, you will come across machine learning almost every day. People are talking about it. The question is, why suddenly machine learning has become so popular or so important? And the reason behind that is a variety of applications in almost all kinds of domains, whether you are talking of medical domain, you're talking of commercial domain, industrial domains, or defense. Everywhere there are applications involving machine learning. And that's why this field has become all of a sudden very, very popular. There are some factors that have contributed to the popularity of this field for the last few years. And essentially, in my opinion, there are three factors that have basically created this hype about machine learning. One of them is cheap data. The data has become so cheap that it's very easy to capture and work with the data. Second one is what I call as algorithmic economy. And third one is the cloud-based solution. According to many of the reports of people who perform analysis about different companies, how the companies are moving in different directions, there are reports that show that every company nowadays can be considered as a data company that is capable of using machine learning in the cloud to deploy intelligent apps for improving their work. That is really what's going on nowadays. And that's one of the reasons why machine learning has become so popular. And as I said, data is getting cheaper. So if you look at the cost of acquiring data or the memory cost, that's how it has gone down. And in terms of how the data is going up, you can see that the data is how much we are storing and how much we are capturing, that is been going up like. And in fact, if you look at Tesla, they have 780 million miles of driving data, and they add about million miles every 10 hours. And that number, by the way, is about 2 years old number. So right now, I'm sure the number is about 2 billion miles. And next thing is algorithmic economy, what we mean by this and why this has become a crucial factor in terms of machine learning becoming popular. Number one, anyone can turn their algorithm into scalable, shareable, production-ready web services. The idea of web services and using algorithms there has really caught on. And if you are smart enough to create an algorithm for something useful, you really don't need a big setup to go and market it. You can create an app and it can be commercialized through web services and the other people can use. So that has become one reason why machine learning has become popular. Make algorithms discoverable. That means you offer them with APIs and in a way that other people can integrate them, use them in their system. So again, that leads to more commercial angle or benefits for the people who are working on these algorithms. And that's another reason why this is becoming popular. And of course, you can monetize them, you can make money out of these. So that's really a big attraction for making machine learning popular. And of course, these algorithms, the way they are being designed and implemented, they are modular. That means you can actually pull out algorithms from different vendors in a way, and you can stack them together to actually do your own solution. In fact, there are a number of algorithms that are available where you can use them via Excel, because Excel is a very popular software in the commercial domain. So you really don't need to know anything about machine learning or anything. As long as you are an Excel user, you can actually perform most of the machine learning tasks simply by calling some of these apps through your Excel. So that's really what has taken on, and that has led to the usage of machine learning as well as its applications are going on right now. All right, so I think I did this without making it up. All right. Another one is what I said is cloud-based intelligence. So there are companies out there that are providing you with a cloud platform, with machine learning software, with deep learning software, and as a user, all you have to do is to take your data to that platform, and then through visual graphical user interface, you can actually create systems that will do the learning for you and produce the results in a way that you can actually download and put them in production. So there are a number of companies that have come out, for example, Data Robert, Amazon Machine Learning, Microsoft, Databricks, and all that. And these opportunities, these platforms also have given rise to the usage of machine learning in almost all the domains that we come across. So let's look at some of the terminology of machine learning. This is one concept that over the years I have found that the students, when they get started in machine learning, they kind of have hard time understanding the idea of feature vector. So in machine learning, the concept of feature vector is really important, and feature vector is really nothing but a representation of the input. The input could be any object, any record, any person, or an event. As an example, in this case, let's say that we want to represent this flower. So we can represent this flower in some of its characteristics. And if we are measuring 4 characteristics like the ones I have shown there, triple width, length, middle width, and length, then mathematically we can represent this flower as a 4-dimensional vector. And that is what we call as a feature. If you look at another example where you want to predict the housing prices, let us say. So different houses can be characterized in terms of the square footage, the number of bedrooms, number of bathrooms, and all that. And if you put all that information for every house in the form of a vector, then basically we can represent an entire collection of houses as a collection of vectors. And those vectors are what machine learning algorithms will use to figure out what are the underlying patterns that are present. In terms of machine learning style, that is basically you're going to be working with lots of data. So how do we discover patterns or relationships from this data? So there are essentially 3 basic styles of learning. Okay. One is what we call as a supervised learning style. In this case, the data comes with known answers. And these known answers are what we call as labels. So the idea here is that you are going to present to the system a set of examples, and for every example, you are going to present the corresponding answer. And the system is then trying to figure out what is the relationship between the input numbers and the answer. And based on that, the system is going to construct some kind of model. And by looking at different examples, the system will refine that model. And that is the model that we end up using for our future examples for which the answers are not known. So that's what we call as supervised learning. And some of the learning models that come out of using supervised learning techniques typically are classification models, where you can use these models to predict customer journey. You can use them to tag objects in images. You can use these patterns to figure out whether an incoming phone call or an email is a spam or not. So those are some of the applications that people use for have found for supervised learning models. Supervised learning models can also be used for doing regression. That is, you want to predict numeric output. In classification, you are predicting categorical output, whether a given customer is likely to leave your service or not. But in regression model, you are trying to predict what is going to be the value of this stock at the end of the day. So those are regression models, and again, one can learn those models using supervised learning. And you could use them to predict credit card balances that the customers will carry, predict the number of likes your posting is likely to get on Facebook or on Twitter, or predict the peak load for a utility given weather information and things like that. So those are some of the examples of supervised learning models using regression models. In many cases, you may not have the correct answers for the data that you have that you want to use for training. So in that case, the training style or the learning style is known as unsupervised learning. So in this case, the data comes without labels. And the basic idea of unsupervised learning is to look at different records or different data vectors and group them based on similarity. That is, if you find number of vectors looking very similar, then you put them in one bin. If you find another group looking very similar, you put them in another bin, and so on. So that is what we call as unsupervised learning. And this is pretty popular in terms of grouping text, documents, pictures, and so on. And also has number of applications. For example, you might be thinking of creating a marketing campaign. And to do that marketing campaign, maybe you want to target only a certain types of customers. So you can do that by performing unsupervised learning so that you can identify different segments of customers and you can create a marketing campaign, but each segment suited to that particular segment. Or you might have a large collection of documents and you may want to organize them into some meaningful groupings. So again, you can make use of unsupervised learning. And of course, it can also be used to make product recommendations, especially if you go to Amazon or many other sites and you're looking for a product. They also say, well, if you're looking for this product, maybe you also want to look for this product and so on. All that is actually the result of unsupervised. There is another learning style that has been around for many, many years, but currently it is very popular, especially given the idea of autonomous driving. And this style is what we call as the reinforcement learning. Again, you have data that is without labels. But in this case, the system is operating in some kind of environment, and based on the actions performed by the system receives some kind of feedback from the environment, and it uses that feedback to figure out whether the actions it has taken are good actions or correct actions, or it needs to modify some. So this is what we call as the reinforcement learning. And this is currently a very popular method for learning. And of course, it has a number of applications like in robotics, in portfolio optimization, having programs that learn to play games on their own, etc., etc. What I like to do is to walk through a very simple example just to illustrate the basic concept of how we actually apply machine learning. And for many of you, this might be a very trivial example because you have worked with a lot more complicated stuff, but it is just meant for illustrating the basic concept of how we will use it. So let us say that we want to build a classification model that is to differentiate between two classes of flowers. One is Iris virginica and another is Iris virginica. So what we will do is we will collect a large number of both types of flowers and have an expert tell us which flower is Iris virginica and which flower is other. All right, so that is, we will collect a large number, and we will label them whether this is type 1 flower or type 2. Next is, the expert will tell us what kind of attribute, or we might think on our own, what kind of property we should be using to describe these flowers to our computer, to our machine learning. So in this case, let us say that we basically use two features, I think. And those features are sepal area and petal area. So if we decide, all right, these two attributes should be good enough for us to differentiate between these two types. What we'll do is we have collected, let us say, 100 flowers, 50 from each row, and we made these measurements. Once we have those measurements, we can plot, since we are working in 2 dimensions, so we can plot the data in 2 dimensions. And this is how the plot looks like. What we have done is we have given 2 different colors indicating 2 different types of flowers. So now if you look at this plot, you can see that there is a reasonable good amount of separation between red circles and between violet circles. That means what we can do is we can think of a line, if we draw it in this 2-dimensional space, such that most examples on top of the line are blue examples, and most of the examples below the line are red examples. This is basically what we have done is we have built a classifier, and mathematically we can write the equation for the line and use that formula given the 2 features to figure out whether a given observation is above the line or below the line and make it. Only thing is, in reality, we don't get to work in 2 dimensions, but we have to work in higher dimensions. And that's where we need to think of techniques from mathematics which will allow us to do some of the things that are equivalent to drawing up the lines or drawing up the curves and so on and so on. Now, if you look at this, you can say, all right, well, this line is doing a good job, but still there are some errors that we are seeing here. So you might say, well, why restrict ourselves to a line? Why not create a boundary like this, which has linear segments moving in horizontally or moving vertically? And if I draw this boundary, maybe the number of errors is very, very small. Now we have reduced the number of errors. Well, somebody might come and say, well, why not we draw this boundary? which has no error. So through these three examples, you can see that given a collection of examples, typically which we call as training examples, we can build a classifier, and if you build a highly complex classifier like this, we can get zero error. But I'm sure everybody in this room will agree with me that this is not a good class, because this classifier has been trained exactly to these 100 examples. And there is no guarantee in future we are going to see only these 100 examples or flowers representing these. All right. That means people say, well, this is a boundary that has been overfit. So when we design classifiers or when we build models, whether for regression or anything else, what we need to do is we need to make sure that we are not overfitting the data to get lowest possible error. So generally, what we want to do is we want to have some kind of trade-off between the model complexity, that is, whether you want to use a linear model or quadratic model or polynomial model or any other complex model, and whether that model is achieving or performing overfitting or underfitting. So typically people take the data and divide it into training set, test set, validation set, etc., and use them for to ensure that you don't do overfitting. And some of this is actually expressed in terms of what is the bias and what is the variance of the model. And basically, those are the properties that people use to indicate whether the model is underfitted, overfitted. The best thing about design can be expressed through this simple cartoon, which is Occam's razor, that is, be guided to your model selection by the principle given in Occam's razor. That is, go for a simple solution as far as possible. Don't make things too complex. And if you follow that advice, generally you will come out a winner or you will come out very well ahead in the game. And there are a number of now model building algorithms that people can use for doing supervised learning, like linear methods. If you think this problem is not a hard problem, can be solved by some kind of linear systems, or KNN classifier, which is K-nearest neighbor classifier, which is a very simple approach and does produce fairly good results. Neural networks, support vector machines, decision trees, ensemble methods, and so on. So these are a number of model building algorithms that people have come up with. And I'll just show you one or two illustrations here, again, through simple examples. In this case, we're looking at KNN. Basically, in the KNN, K indicates the number of neighbors. So let's say K is 1. So we are talking of nearest neighbor classifier. So basically, given a test case, what you do is you find out what is the training case with which this test case resembles best. And whatever label is, or whatever you did for that training case, you do that for the given test. The very simple concept, walks like a duck, talks like a duck, must be a duck. Or a lot of people say, you are known by the friends you keep. So that's basically the idea in nearest neighbor search. You simply look at the training examples that are most similar to the test examples and base decision on them. The other model that I want to illustrate is a simple decision tree model. So if you look at data here, which is now in 3 colors, that means we are looking at data in 2 dimensions. So, but 3 classes. So we have 3 kinds of flowers now, let's say, and we still are making those 2 measurements. And when we plot them, this is how we end up. Now, what we can do is we can differentiate between different classes of patterns. For example, we can look at some number here, this pedal width, if it is less than 0.8, must be this kind of. And then we can kind of look at something like here or something like here and sort them out. So this series of steps can be illustrated in the form of a tree structure. So that's what we call as classification modeling. Of course, in this case, we are building the tree by looking at it, but think about, data in 50 or 100 dimensions, when you need an algorithm which should be able to figure out what are the axes to look at, what are the points where we need to put cutoffs and all. So all that has to be done automatically. All right. So that will be the decision tree method for building the things. In terms of unsupervised, the most popular method is k-means clustering, but there are a number of other methods that are also used there. Self-organizing feature maps, recommendation systems, etc. And I'll just very quickly mention k-means clustering. Basically, you have a collection of points in a high-dimensional space. You specify how many groups you want to form out of those points. So K stands for the number of groups you want to form. And basically, you initialize each group through some arbitrary value. And then what k-means clustering does is that it goes through all the examples and assigns them to different groups based on your initial grouping of the initial specification of the centers for each group. And once it has gone through that, it updates the centers and repeats this process. And this process goes on in several times till everything kind of stabilizes. That's really a very simple algorithm and quite popular. So that's basically shown here. And it can be shown that mathematically while doing so, what you're doing is you are minimizing this optimization stress. In terms of recommendation systems that you come across at Amazon and other places, basically the idea, again, clustering is being used, but now you can do the clustering of users based on their attributes. And if Professor Singh likes certain kind of, let's say, food, and his attributes are very similar to my attributes, then chances are that I will also like that kind of. Or if there is an object whose attributes are similar to another object, and if I like object A, chances are that I'm going to like object. So recommendation systems are built around user profiles, object properties, and things like that, or their combinations to figure out what a particular user is going to do. So that's just a cartoon here to show you that, we are reaching the age where the systems will tell us what we should eat. And of course, they will be driving us around. So with that introduction to machine learning, let's look at what's deep learning and why do we need deep learning. It turns out that machine learning methods operate on manually designed. That is, this feature vector that I mentioned in the beginning, those feature vectors are based on properties that the designer thinks are useful for a given task. And it turns out that that approach works very well for a large majority of tasks. But there are problems where the design of such handcrafted features becomes progressively difficult as you start scaling your complexity of the classification model or regression model to a large number of possible classes and things like that. So essentially, for the last 40, 50 years, people have worked with manually designed features in the domain of computer vision, in the speech processing, signal processing, text processing, etc. And with those manually designed features, people have been able to achieve certain level of recognition accuracy. But people realize that there is a ceiling in terms of the accuracy that you can reach. So what has happened is that people have gone of those things is pretty obvious. If you are working with pictures, as Professor Singh mentioned right in the beginning, it is very hard to go from the numbers that are shown at the bottom, which basically reflect a small part of the motorcycle, and think that these numbers represent some kind of part that belongs to a motorcycle. The gap between the number and the concept is so big that it is essentially very difficult to figure out how to achieve that. Also, when you are talking of vision and other similar problems, you could design a system which will work very well, provided you ensure that the lighting is good and the camera and the objects have fixed geometry. Typically, in a manufacturing, maybe on a conveyor belt, etc., you can do that. But if you want a system which can roam around and figure out things, recognize things, obviously, it's going to be a very challenging task because viewpoint variations are so fantastic that whatever system you design for one viewpoint, if you change the viewpoint, the system is likely. So you want something that is independent of viewpoint. You want something that is independent of illumination. So these are all challenges that are present in systems that have to interact with the real world through visual and other senses. Another thing is, if you want to define what is a chair, again, there are so many different variations in the chair, then it becomes really hard to see what is a chair. So, as a result of these difficulties, people have come up with end-to-end learning. That is, what you do is, you have a large amount of data, and you have a network at which you throw this data in its raw form and let the network figure out what features it should be extracting and using to perform a classification or to perform any other task. So deep learning is basically nothing but end-to-end learning using a series of neural networks or series of layers of neural networks. And basically, you work with the raw data, and of course, you do the supervised learning. That's what you're doing. Then for every raw data example, you provide the correct answer that the system is supposed to. Okay. So basically, I look at deep learning as a subfield of machine learning that has shown remarkable progress in dealing with applications requiring processing of pictures, videos, speech, text, etc. I think these are the domains where deep learning is really good and characterized by extremely large amount of data for training, neural network with exceedingly large number of layers, training time running into weeks in many instances, and of course, end-to-end learning, that is, no human design tools or feature shop. So these are some of the characteristics of deep learning that have made it popular, and there are a number of deep learning models that are out there. One of the early ones and most popular model is what we call as the convolutional neural network, which basically has a series of layers where each layer performs certain kind of convolution operation on the input data, and those layers are progressively made smaller and smaller, so that what you are doing is you are starting from the very raw features that you're extracting in the beginning and slowly building a higher level abstraction of those features. And some of the networks that people have built, and they have looked at what kind of features they are building. So they have figured out, or they have shown that in the early stages, the system is learning to build features that are basically edges and blobs. Later layers, it's building some features that basically respond to texture. Then it is looking at some other stages, it's building features that are groupings of earlier features, and progressively that grouping goes on. And towards the end, typically you have two layers which are called fully connected layers, where you basically use the supervised learning labels that you have provided to figure out what is the output that is being produced, and then you feedback the error all the way back to the first layer and adjust the weights. So that's a model that has become very popular and has been used for doing all kinds of classification tasks. Many applications involve, like if you're doing speech, what happened earlier, or if you're working with text, whatever text words you're looking now, they are basically dependent on what words you saw. So for those applications, there are recurrent neural networks that have a history component in them, and typically these networks have been used for applications involving speech processing, stock market forecasting, time series analysis, text processing, and things like that. And there are networks known as deep Q networks. These are the networks which basically rely on reinforcement learning. And these networks can learn to play games. And some very interesting results have been obtained using these networks. And I'm just going to show you some examples of the work that people have done. For example, through convolutional neural networks, you can take a street scene and you can identify different objects in the scene. And this is essentially useful for autonomous driving and things like that. In terms of recurrent neural networks, there are applications involving real-time translation. For example, you might have a system, like Microsoft has a system which can do English to Chinese and Chinese to English in real time. So if you are an English speaker and you don't know Chinese, you go to China, if you have that system, you will be able to do communication with other people. And here is an example of the network that learns how to play games. And the most famous there is AlphaGo network that basically is shown to surpass the capabilities of some of the world level players after 3 days of training, etc. So, and these networks learn on their own how to play games. So that's again is very useful, especially because if you think of autonomous driving, as an engineer, you can't think of all possible scenarios the vehicle is likely to encounter. That's where you need reinforcement learning so that it can figure out on its own in a situation what needs to be done. Training basically, the workhorse is still the back propagation algorithm. And essentially, training consists of optimizing the performance. So a lot of people tend to say that deep learning is really nothing but optimization. And to a great extent, they are correct. That is what you're doing is you are having a system, you're defining the performance, and then you're looking for parameters that will optimize it. Some of the more examples, for example, people have used deep learning to automatically generate captions for pictures based on some of the properties that are seen in the pictures, and of course based on supervised learning to build a model that generate those descriptions. People are using it in the medical domain to predict onset of heart attacks, etc. A lot of use is being made in terms of building chat interfaces so that as a consumer you think you are talking with somebody, but you are really interacting with the software on the other end. You might say, well, why deep learning has become so popular in the last few years? The answer is better hardware, large volume of data because of the internet. Earlier, people could not collect that much of data. And of course, there were certain tricks that people made in terms of back propagation. People knew earlier that you could have many layers and get better results, but they were never able to figure out how to train networks with large number of layers. So some of the tricks that people have made in the last few years have resulted in being able to do that trick. And those tricks essentially revolve around changing the activation function, etc. And those tricks have given rise to all these networks where you can still use 100, 120, 140 layers in the training. Another thing is transfer learning, that is, in many applications, you really don't need to start from scratch. There are trained models out there that you can download and you can modify those models very quickly to your own application. So you don't really need to spend weeks and months training a model. You take a trained model and through transfer learning, you can fine tune that model to your application. So that is also helping deep learning getting more popular. Of course, I don't know, but if you read the literature, you will come across a complaint that there is a learning bias. That is, these systems are learning from examples, so whatever bias is there in the examples, these systems are going to show that bias. And that is so true. And there's an interesting story here, way back when the neural networks came out, about 30 years ago. DARPA had a big project to do text identification or recognizing text in the images. And the project showed very good results on the training data, test data, etc. But when it was put into real life use, it failed because the images that they had captured basically had mostly taken on the cloudy days, and somehow that bias, cloudy days, basically hindered the performance. All right. But there are some very interesting examples nowadays in terms of the learning bias. For example, Google mistakenly has done some tagging of black people as gorilla, etc., and they had to actually take down those algorithms. Or Microsoft, I think 2 years ago, they did a big announcement. They had put out a chat system that will allow people to converse with it. But within a day, they found that through conversation, the chat system basically has learned to use all the bad language and all the bad words and things. And of course, there are a lot of complaints about the Apple's Face ID because it fails to recognize the Chinese users, whether they are, it's looking, many of them are saying they're the same, or it's failing to do the gender identification and things like that. Also, these networks are trained with large examples, but sometimes people have shown that these networks are really not doing any real learning. Somehow or other, they are capturing the variations in the data and using that, but while capturing that, they are not really capturing relationships in those different elements of the data. And the best example there is actually, these are the examples. For example, people have trained systems for doing the digit recognition where the digit part is bright and background is dark. Now, people have shown that if you flip it, the system doesn't work that well. Or you take this image of a very famous model here, and if you just take the eyes and place them at different places, do some changes, the system still thinks it's that person. So it's not doing a good face recognition. It's not thinking that for a proper face recognition, the eyes have to be in a symmetrical fashion and nose has to be in between and things like that. So in somehow or other, there are issues in terms of what is being learned, or some people say these are issues related to architectural differences, and there are a number of people trying to address many of these. So just to summarize, I think we are getting close to 2 o'clock, and I put time to summarize. So basically, machine learning and deep learning are growing in their uses. Many of the ideas have been around for a long time, but are being put into practice now because of the technology progress. There are a number of open source software resources, R, RapidMiner, Scikit-learn, PyTorch, TensorFlow, etc. One can make use of these resources, number of postings, examples out there on the web to learn via experimentations. Applications based on vision, speech, and natural language processing are actually excellent candidate for deep learning. And of course, there's always a hype, so one needs to filter the hype from reality. And to capture that sense of hype, there is a statement from Nobel laureate Hermann Simon, which he said in 1965, that machines will be capable within 20 years of doing any work that man can do. And we are yet to reach that level of performance. So at this, I like to conclude and thank you all of you for.
Thank you very much, Dr. Shetty. I think it's a really highly informative seminar.